Hey everyone, and welcome to another deep dive. Today we're mixing things up, literally. We're diving into the fascinating world of thermodynamics.
Specifically, how different chemical species decide to mingle or play hard to get.
And we're not just like stirring things up in a beaker here.
No, this is about understanding the fundamental forces that govern how materials blend at a molecular level,
Okay, so we're getting really small then.
with a special focus on polymer solutions.
Polymers, huh?
Okay.
Okay, that's where things get a little outside my comfort zone, I'll be honest.
These are really interesting, though.
I did skim the textbook chapter you sent,
Okay.
and it mentioned things like polystyrene and polybutadiene.
Yeah.
It sounds like the ingredients for a science fiction smoothie, right?
Well, not quite a smoothie, but you're on the right track thinking about ingredients.
Polystyrene and polybutadiene are both polymers. Those long chain-like molecules that make up many of the plastics and rubbers we use every day.
So instead of blending fruits, we're talking about blending these long molecular chains.
Exactly.
And this chapter, it's all about why some blends mix beautifully.
Some do, some don't.
Some separate like oil and water.
Right.
And some just, I don't know, do their own thing.
Exactly.
Yep.
And the key to understanding these mixing mysteries, it lies in a few key concepts.
Okay, Leonie.
Entropy,
Yeah.
energy of mixing.
Right.
Something called the Flory-Huggins theory, which, trust me, is way more interesting than it sounds.
Okay.
And those visual roadmaps, phase diagrams.
Okay, phase diagrams sound a little intimidating.
Okay, yeah.
But I'm ready to unpack it all.
Right.
Let's start with the basics. What drives mixing in the first place? Is there some kind of molecular mixer that gets these substances grooving?
Well, there's no, like, tiny DJ in our beaker. But there is a fundamental force called entropy that loves to mix things up.
Okay.
Think of it this way.
All right.
Imagine your room.
Oh.
Left to its own devices, does it tend towards neat and tidy or gloriously chaotic?
Definitely leaning towards the chaotic side, much to my mother's dismay.
Exactly.
Yeah.
Nature, it turns out, has a similar penchant for disorder.
Really?
That's entropy in action.
Oh, okay.
There are simply many more ways for things to be mixed up than perfectly organized.
So more possibilities for a mess than to be organized.
Yes, so on a molecular level, entropy pushes things toward mixing.
So it's like nature's way of saying, let's shake things up a bit.
Precisely.
Well, I kind of like that.
And to visualize this, scientists use something called the lattice model.
Yeah.
Picture molecules as little balls fitting onto a grid, like a microscopic chessboard.
Okay.
When you mix two different types of molecules, suddenly there are so many more possible arrangements.
Right.
So much more disorder,
So more entropy.
and therefore higher entropy.
So more spots on the chessboard for our molecules to occupy.
You got it.
But I mean, those diagrams in the chapter, they show real molecules, not just like neatly arranged balls, right?
Right.
Like, how realistic is that?
Real molecular interactions are much more dynamic.
Okay.
Molecules are constantly wiggling and interacting, not stuck on a grid.
Right.
But the lattice model gives us a simplified way to grasp this concept of entropy and how it favors mixing.
Okay, that makes sense.
Yeah.
The chapter also mentioned different types of solutions,
Yes.
like regular solutions, polymer solutions, and polymer blends. What's the difference?
So it all comes down to size, really.
Okay.
In a regular solution, all the molecules are roughly the same size, occupying similar amounts of space on our imaginary lattice.
You're right, I'm picturing it.
But polymers, those long molecular chains, can sprawl out over multiple lattice sites.
Okay, so they're not just taking up one spot on our chessboard.
Right, and this size difference drastically changes the entropy game.
So size matters in the mixing world.
It really does.
That's interesting because if a single polymer chain takes up the space of, say, 5 smaller molecules, wouldn't that mean there are fewer ways to arrange them compared to just a jumble of smaller molecules?
Exactly.
So less entropy.
You've hit on a key point. Because polymers are larger and more interconnected, they have less freedom to move around, which impacts the entropy of mixing.
Okay, that makes sense.
Think about it.
Yeah.
Mixing 50 individual small molecules gives you a lot of possible arrangements,
Right. Tons.
but mixing 5 long polymer chains, significantly fewer options.
Yeah. Okay.
Yeah.
So entropy loves to mix things up.
It does.
But polymers, because of their size, introduce a bit of a wrinkle.
They do.
Is that what an ideal mixture is all about?
Yeah, so an ideal mixture is like the utopian society of mixing, where
Right.
everything blends perfectly based solely on entropy.
Okay.
But just like in the real world, things aren't always that simple, especially when it comes to polymers.
Right, because even those long-chain polymers, like, they have preferences too, right?
You could say that. And that's where the energy of mixing comes in. capturing the attractions and repulsions between molecules.
So we're not just talking about random mixing anymore, but actual molecular compatibility.
Yeah, it's like a microscopic dating game.
How do we even measure these molecular preferences? Is there a Tinder for molecules?
I wish it were that simple. But there is a handy tool we use called the Florey interaction parameter,
Okay.
often represented by the Greek letter chi.
Right. I remember that from the chapter.
Think of it as a compatibility score for molecules.
Okay.
A positive chi value means the molecules would rather stick with their own kind, like oil and water famously do.
Ah, oil and water, the classic example of a molecular mismatch.
Yeah, high chi value for sure.
So a negative chi value would mean that the molecules are actually attracted to each other and want to mix.
You got it? And this little chi parameter is a big deal
Yeah.
because it helps predict how real polymer blends will behave.
How so?
Will they form a strong, stable material, or will they separate and crumble?
So, like, is this going to work out long-term, or is it going to be a disaster?
Exactly.
I
And those phases, that's where things get really visually interesting.
Okay.
Imagine a map that shows you all the different ways a mixture can exist at different temperatures and compositions.
Okay.
That's a phase diagram in a nutshell.
I like where this is going.
But we'll save that adventure for part 2 of our deep dive.
You're killing me. All right, fine. We'll have to wait for part 2 to see what these molecular maps look like and what secrets they hold. Until then, thanks for joining us on this deep dive into the thermodynamics of mixing.
So last time, we were mixing it up in the world of polymers.
We were in the thick of it.
We talked about how entropy loves a good molecular party,
Right.
but those picky polymers have their own ideas about who they like to mingle with.
Right, like a molecular high school dance.
Yeah.
Where entropy's trying to get everyone on the dance floor,
Right.
but some polymers are clinging to the punch bowl with their friends.
I like that analogy. And just like a good high school drama, things get even more interesting when we bring in the concept of phases.
Okay, phase diagrams.
Yes.
You promised those would be visually interesting.
I did.
I'm ready to see what these molecular maps look like.
All right, let's pull up figure 4.8 from our trusty textbook chapter.
Okay, got it right here.
This diagram shows what happens to a blend of two polymers at different temperatures and compositions. Think of it like a treasure map for polymer scientists.
Ooh, treasure map. I like it.
Instead of buried gold, we're looking for regions of stability where our polymer blend is happily mixed,
Right.
and regions of instability where it wants to separate.
Gotcha. Okay.
Now see this curve on the diagram?
Yeah.
That's called the binodal curve.
Binodal.
And it's like the coastline separating those calm seas from the stormy seas.
So above the binodal curve, our polymers are all happily mixed.
They are.
And below it, we're headed for a molecular storm.
You got it.
Okay.
Now look closer.
Okay.
There's another curve inside the binodal curve called the spinodal curve.
Binodal. Okay.
This one marks the difference between a mixture that's merely metastable.
Metastable.
Think of it as nervously holding its breath.
Oh.
And one that is truly unstable and ready to spontaneously separate.
So metastable is almost more dangerous then.
It can be.
It's like it looks fine, but who knows what's going to happen?
Exactly. A metastable mixture might look homogeneous, but it's teetering on the edge.
Yeah.
Any little disturbance,
Yeah.
a change in temperature or pressure, and bam, phase separation.
So outside the spinodal curve, it's like those polymers are holding hands on a roller coaster.
The laughs.
One good bump and it's all over.
Pretty much.
Okay.
But within the spinodal curve, there's no holding on. Those polymers are going their separate ways no matter what.
So you don't even want to be anywhere near that spinodal curve.
Not if you want your blend to stay mixed.
Gotcha. And what about that point at the very top of the spinodal curve?
Yeah.
It's kind of lonely up there.
That, my friend, is the critical point. A special combination of temperature and composition where the distinction between the two phases simply disappears.
Oh, interesting.
Above that point, it's all smooth sailing, complete mixing no matter what.
So it's like the polymers have reached molecular nirvana.
Precisely.
No more drama, just pure blissful mixing.
And understanding these critical points is crucial for predicting how well different polymers will mix.
Okay.
But remember that osmotic pressure we talked about earlier?
Yeah, we measured it in the lab.
It's not just a cool lab measurement. It's directly related to these phase diagrams and the Florey-Huggins equation.
Wait, really? So by measuring how badly a solvent wants to dilute a polymer solution, we can tell if the polymers are going to get along or stagiomolecular breakup.
Exactly.
Wow, that's really cool.
A high osmotic pressure means strong interactions between the polymer molecules, which usually translates to a higher chi value, remember?
Right, a high chi, those polymers prefer their own company.
Exactly. And if we go back to our phase diagram, a high chi value means those polymers are more likely to separate, to have a larger region of instability.
Okay, so osmotic pressure isn't just some abstract concept. It's a peek into the hidden world of those molecular relationships.
Precisely.
This is really cool stuff, I have to say.
It is.
And this is why understanding these, what seemed like complex equations and diagrams, is so crucial.
Right.
They give us incredible predictive power in the real world.
Exactly.
Okay, so we can design things better, we can make things stronger, all by understanding how these polymers are going to act.
Exactly.
This is fantastic.
But what about those situations where we're dealing with very low polymer concentrations?
Right.
Does the Flory-Huggins equation still apply, or do we need a whole new set of tools?
Yeah, because we were talking about those polymers being all crowded on that lattice.
Right.
What if they have tons of space? Does it still work the same way?
That's a great question.
Yeah.
The Flory-Huggins theory, as powerful as it is, does have its limitations.
Okay.
It works best when those polymer chains are rubbing shoulders on our imaginary lattice.
Right.
But when they're at very low concentrations, swimming around with lots of space between them, we need a different lens.
So it's like the difference between understanding the dynamics of a crowded party versus a few people scattered across a park.
Exactly. When we're talking about dilute polymer solutions, the focus shifts to individual polymer chains and how they behave in a sea of solvent.
Okay.
And one of the key concepts here is excluded volume.
Excluded volume. Okay, so what's being excluded and from where?
Imagine each polymer chain has a personal space bubble,
Laughs.
a volume that it occupies and prevents other chains from entering.
Okay.
That's its excluded volume.
So it's like each polymer chain has its own little dance floor and no one else is allowed to step on its toes.
You could say that.
All right, I like it.
Now, the size of this dance floor, or the excluded volume, depends on how much the polymer likes the solvent.
Okay, so we're back to those molecular preferences again.
We are.
Is there like a good solvent and a bad solvent?
Absolutely. A good solvent is like the life of the party.
Okay.
The polymers want to mingle, so their chains stretch out, taking up more space.
Yeah.
A bad solvent is more like a wallflower. The polymers would rather stick to themselves, so their chains collapse into compact globules.
Globules, okay.
Yeah.
So they go from these sprawling chains to these tightly wound balls of yarn, essentially.
Exactly.
And this all depends on the solvent.
It does.
That's wild. Polymers are more sensitive than I thought.
They can be.
This is making those phase diagrams even more fascinating.
And this solvent quality can even change with temperature.
Oh, really?
A solvent that's good at a high temperature might become bad as things cool down, causing those polymer chains to dramatically change their behavior.
Wow, that's a recipe for disaster
It can be.
if you're not careful.
It can be.
So we've got these globules in bad solvents.
Yes.
But what happens when things get really crowded, when those globules start bumping into each other?
Excellent question.
They can't all be wallflowers forever, right?
That's where we enter the intriguing world of the semi-dilute regime,
Semi-dilute.
a kind of twilight zone between a dilute solution and a concentrated polymer melt.
Okay.
But we'll save that adventure for part 3 of our deep dive.
You're killing me with these cliffhangers, but I'm hooked. We'll be back soon to explore this mysterious semi-dilute regime and see what other secrets are hiding in the world of polymer solutions.
All right, back to the dance floor for part 3 of our polymer mixing extravaganza.
It is getting crowded in there.
And this time things are about to get crowded because we're entering the semi-dilute regime, right?
It's a bit like that moment at a concert.
Oh.
When the crowd goes from comfortably spaced to, whoa, I think my arm is touching a stranger.
Okay.
Still dissolved, but definitely feeling the presence of others. Okay, I'm picturing it, so no more isolated globules.
Not so much, no.
Those polymers are packed in tight.
They're getting there.
But you said it's not quite a solid melt yet?
Exactly. Think of it as a transition zone where those individual polymer dance floors we talked about, they start to overlap.
All right, so they're bumping into each other now.
A little bit.
Okay.
And to navigate this crowded space, we use a new measuring stick. The correlation length.
Correlation length.
Yes.
What is that? Is that like the average distance two dancers can travel before bumping into each other?
Precisely. It's the distance over which those polymer chains can still wiggle around without feeling the influence of their neighbors.
Oh, hi.
As the concentration increases, more polymers in the mix, that correlation length shrinks.
So as the dance floor gets more packed, those polymers have less and less personal space. What happens then? Do they start a mosh pit?
Not quite a mosh pit,
Perhaps.
but this crowding does have some interesting effects.
Like what?
Remember viscosity?
How easily a fluid flows.
Yes.
Like water being low viscosity and honey being, well, not so low.
Exactly. As that correlation length decreases in the semi-elute regime, those entangled polymers, they increase the solution's viscosity.
So it gets thicker.
It becomes thicker, more resistant to flow.
So that's why some polymer solutions have that gooey, almost gel-like consistency.
It very much is, yeah.
It's those entangled chains clinging to each other.
Exactly.
But this isn't just a cool science experiment, is it? There must be real-world applications for this.
Absolutely. Think about paints and coatings, even food products.
Oh, okay.
Controlling that thickness, that texture is crucial.
Right, I wouldn't want lumpy paint.
And understanding the semi-dilute regime helps scientists fine-tune those properties.
So no more lumpy paint or runny yogurt, all thanks to polymer physics. Who knew?
I mean, that's kind of what we do this for.
But what blows my mind is that this semi-dilute regime isn't limited to specific polymers or solvents.
Yeah.
You said it exhibits universal scaling behavior.
Yes, it does.
What does that even mean?
It's one of the most fascinating aspects of this regime.
Okay.
At these concentrations, the individual details of the polymers and solvents matter less than the overall behavior of those entangled chains.
So it doesn't matter if they're wearing a lab coat or a party hat. It's all about how the crowd moves as one.
Exactly.
That's really cool, so we can apply these rules more broadly.
And because of this universality, we can predict how properties like viscosity will change with concentration using something called power laws.
Power laws.
Elegant mathematical relationships that hold true across different systems.
So even though these systems can be so complex, we can still describe them with these elegant laws.
Exactly, the power of math.
I am blown away by the elegance of polymer physics, I have to say.
It's an amazing area.
Who knew that such complex behavior could be described by these, seemingly simple laws?
It's quite remarkable, and it highlights the power of understanding these fundamental concepts. Entropy, energy of mixing, correlation length, to unlock the secrets of these intricate molecular dances.
We've gone from those tiny molecules arranged on an imaginary chessboard to crowded dance floors and universal laws of behavior. This has been quite the deep dive.
I agree. A lot of really cool stuff.
And we've only scratched the surface of the vast and dynamic world of polymer solutions.
There is so much more out there. It's a huge field.
Well, if this is just the surface, I can't wait to see what lies beneath. But for now, I think it's time to let our listeners digest all this incredible information.
Hopefully this has inspired people to go and learn more.
I hope so too. And on that note, thanks for joining us for this deep dive into the fascinating world of the thermodynamics of mixing. We'll see you next time for another exciting exploration into the depths of science.